k-nearest neighbor search algorithm finds the most similar items to the query. It is widely used in recommendation systems and web search engines. It goes as follows. Suppose we have 9 points. Each point represents a person. Name, age, height is embedded into a vector. And we want to find the most similar person to Q. The algorithm will loop through all the points and calculate the square distance of vectors between Q. The point that has the closest distance to Q is the one we want to find. But the problem is that the time complexity is linear. As the points get more and more, it would be infeasible for this approach to return a result in ideal time. So, is there any way to make it faster?
So, before investigating the algorithm, let me first introduce a concept named small world network. Every person in the world can be reached by any other person within 6 social connections. It refers to a random person A that wants to find a random person B. So, instead of finding directly B, it will first asking its neighbors C and D. And then, D will help A to find B by asking his neighbors E and F. Then after 6 such actions, B will be found. So, here comes the NSW graph that is founded based on this concept. Instead of graph like this that points are connected to each other, navigable small graph refers to points that only connects to its nearest neighbors. Therefore, if the point wants to traverse to this point, you only need to traverse through a series of small edges, and which assure the navigability that every node can be reached by any other nodes within NSW graphs. HNSW stands for Hierarchical Navigable Smaller Graphs. Compared with NSW, HNSW includes the concept of skip list to ensure a long-distance traversing at an early state of searching, and then short-distance search for the k-nearest neighbors. Suppose there is a random person A who wants to find a random person Q. Instead of directly asking its neighbors, as in NSW, the whole world will first be randomly separated into different layers. The people in upper layers also exist in lower layers, but people in lower layers doesn't necessarily exist in upper layers. So A will first start by asking its neighbors in the current layer, which is B. Then B will repeat the asking actions until they fail to find any other person who knows better than themselves about Q. After that, B will need to travel to a lower layer to find people who knows better about Q than himself. And when they finally travel to the lowest layer, they will find the K people who know the most about Q among the whole world.
Remember in the mailgram experiment, we talked about forwarding mails from Nebraska to Massachusetts. In each step, the mail being forwarded to someone the holder knows on a first-name basis. In reality, a person may know and ask for multiple people, but only 1 or 2 may be useful in the end. We believe by gathering and use extra information, the people being forwarded to will tell the original holder whether or not he successfully sent to the recipient. The small world graph will become more navigable. We explore the intrinsic structure of the graph and we observe the similar phenomenon that some edges might be particularly useful. By removing unuseful connections, we find great potential to reduce query time by an estimation of 10 to 20%. We plan to propose a more powerful algorithm to make querying faster based on this idea.